JNCASR, that's in Bangalore, and that was back in 2015, and then he moved on for a Newton International Fellowship. That's from the Royal Society London, and he worked with Prof Sir Richard Friend at Cavendish Laboratory. That's in University of Cambridge, UK. He also worked at UKRI-research associate at Cambridge University on the INDO-UK solar energy project till he came here and joined as an assistant professor. His research includes physics of optoelectronic devices using solution-processable metal-halide perovskite semiconductors and also polymer semiconductors and other materials. So he is going to talk today elucidating nanoscale optoelectronics in novel semiconductor devices with ultrafast spectroscopy. So I request Ravi to...
I'm going to talk today some of the results which I was doing back in Cambridge. I'll be explaining this, and the title, as I mentioned, it's about looking at this novel semiconductor and look for the nano optoelectronics. So some of the these perovskite which we go to the nanoscale, we make some 2D kind of perovskite, and then we'll try to extract the optoelectronic properties of that. So in this today's talk, I'll be basically first introduce just to make a colloquium level seminar of what is about this metal, organic, inorganic metal halide perovskite systems are. And then I'll move on to use some ultrafast spectroscopy to address how we can enhance the photovoltage in the solar cell, and for a LED application, how we can make a 2D based perovskite for a high illuminating electroluminescence from the LEDs. And then I'll move on to some other interesting photo detector, which is a single pixel color sensor. Then I'll go to look for some optoelectronic properties of this using a different technique, which we call it as which we use as a time dissolved photoluminescence technique, which I'll explain on that, on some of these perovskite crystals. And later I'll finally end by looking at the important drawback of this perovskite materials and how we are addressing them. For example, the ionic conductivity of this perovskites are pretty huge, and how we can rectify it, or how we can modify the system so in order to get good optoelectronic devices. So to start with, just a motivational slide. So if you see at the we all know that our petrol rates are going up because of the crude oil, and there's a very rapid growth in our energy demand throughout the globally, and also there is a near depletion of fossil fuels. So what we have to look for some renewable sustainable source of energy, and one such is the solar energy. And if you see the solar irradiance map across the globe, where we are at almost like more than average of solar irradiance illuminates on India. For example, the number is around 2000 kilowatt hour per meter square itself. So which is like above average of solar irradiance. And if you look at the energy basket, current energy basket, how much we are using as a solar cells in our basket is mostly dominated by coal based products, which is more than 50%, like 49, and other lignite, which is like 50% of it. And again the fossil, gas and diesel, which also covers another 6%. And other renewables are like hydro, wind and solar covers other part. And it's interesting that our renewable part, like just 5 years back, we were only around 6%. Now India has ramped up its renewable energy parts, and we are going ahead with almost reaching 30%. So in that, the solar energy, we are currently at 13% of the overall basket, but we have still more to achieve, where for a goal of 2020, we would like to have almost like crossing more than 80% of solar based renewable energy sources. So if you look at the photovoltaic technology, there has been an evolution. So the early 1960s and 70s, when this started out with the photovoltaic technology, it started with the crystalline silicon based system. Basically it's a silicon, both crystalline and the multi-crystalline systems has been used in order to fabricate some of the first generation of photovoltaic devices. But there is an important drawback for that. That is because of the intense fabrication process, such as like the annealing temperature goes almost more than 1000 degree for doping levels, or even goes up to 1500 degrees centigrade during the processing of P and N junction. So which makes it a very energy intense process in order to fabricate it. And then it comes across the thin film solar technology, which basically use SIGs and cadmium tellurium based system. But again the drawback is it's a rare materials, so again the cost of the system will go high. And then comes the third generation, that is what from the past 1.5 decade which we are looking at, is using some organic semiconductors, which are basically a sp2 hybridized conjugated molecules, which can photoactively absorb the photons and then generate your charges. And along with that, there is also a concept of dye sensitized solar cell, which works on the same basic principle. And also we come across quantum dot based, and now is what we are mainly focused on, the hybrid perovskite, organic inorganic hybrid metal halide perovskites. So why we want to go ahead in this direction is because of one important part is the low cost production and easy installation, logistics, all this comes, but the important part is the low cost production. You don't need more than 100 degrees centigrade in overall process while you are making these devices. So that's a...
How does it compare per watt? How much money you have to spend to make a watt of power?
I'm going to put that...
And the cost is one small portion of all these things. Right?
I'm going to put that slide just next year. That's about the energy payback time. So that's an important parameter one has to look. So in all this third generation system, as I mentioned, it's not only the low cost of the molecule, it's also the production process itself is pretty low. One can envisage that it can be made into an A4 size printer, putting a proper kind of ink, and ink basically means the photoactive materials and also some buffer layers where one can basically print your solar cells and you can put out on the rooftop. So that's a very forefront thought of doing that, but currently in a laboratory scale one can do a roll-to-roll processing of this solar cells, and that's an important point to sell it out. As the sir was asking, what is the energy payback time for any technology in any energy source? When we have to talk about what is the energy payback time, which basically saying how much energy you have put in by building it or starting out the system, and how much energy it has to, how many days or how long it takes in order to give back such a same amount of energy. So basically, if you look into that, the silicon comes in the range of like 1.5-ish in a different aspects to consider to go all the way up to 3 years. Whereas the cadmium was relatively low and 6, but if you consider the perovskite based, the range starts from 0.3 years all the way up to 0.6 years. So it's like 4 months of what you fabricate. Within 4 months you can get back whatever the energy you have put in making those panels. So that's a selling point of using this. Particularly the third generation based. Even for a conjugated based molecules such as organic PVs, it is also noted that it can also go down to 24 hours, like 3 days of solar illumination, considering 8 hours of solar illumination per day. So with this background, I'll go to just brief up about what are these optoelectronic devices. So basically we have two devices which generally everybody already touched upon. One is the solar cell, another one is the LED. LED is everybody in their mobiles they are having, and both works reciprocate to each other. So in the solar cells, basically the photon illuminates on the semiconductor and excites the electron from the valence band to the conduction band, and this will be extracted onto the external circuit. Whereas in the light emitting diode, you are going to inject both electrons and the holes to the system, and it will be recombined in the semiconductors to emit the photons. So that's a basic principle which works well. Even though those look similar, but the device architecture and the fabrication procedure and the working principle also drastically changes when we really work into the real world LEDs and solar cells. We'll come across some of them. So in this talk, I'll be using some of the data which has been acquired using transient absorption spectroscopic technique, which basically it's a 2 pulse femtosecond pulses which are in the order of hundreds of femtosecond pulses. One is a monochrome pulse, which we call it as a pump, which basically excites the sample, and other one is a polychrome probe, which basically looks at what all the changes which has happened after the excitation has occurred. So to the probe pulse, we generally insert a delay by a translation stage, which leads us to see the complete evolution of what all the excited state changes which is happening, which basically telling you the evolution of or the kinetics of the excited state species, for example polarons, excitons, and something in those lines, even the charges in inorganic semiconductors. So I'll be using this technique in order, I'll show some of this data in the further slides in order to explain some kinetics which we have seen in those systems. So now let us come back to this organic inorganic metal halide perovskite. People who are working on perovskite will know on this, but I'll put across all the basics of what it is. As the name suggests, it's a perovskite, it's an ABX3 compound, and the important part is this B is a metal and X is an halide, and A is the important part, where A can be a small organic moiety such as methylamine or a form of indenium amine or a guanidinium amine. So it can fit in this same ABX3 compound. Because of this organic inorganic nature, we can actually basically make into a salt solution, and we can spin coat and try to make a polycrystalline film. For example, here the spin coating can be done and on any glass substrate, and it can be annealed at only around 100 degrees centigrade, where you will finally end up very high quality polycrystalline semiconducting films. So why we are so interested on this semiconductor is because of its very high optoelectronic properties. For example, we need a very strong absorption coefficient of this semiconductor, which is like greater than 10 to the power of 4 centimeter inverse, and their carrier lifetimes are greater than 1 microsecond, which is like equal to our inorganic silicon based system, and electron hole diffusions are reported to be more than 1 micrometer, and the carrier mobility, this is important, is also in the order of 1 centimeter square per volt second. So these are like giving us a clue that this is a tremendous application in terms of optoelectronic devices. So yes, people have started initially doing solar cells and LEDs, and there has been a drastic increase in its numbers. For example, this is the record efficiency versus the years. We can see all this silicon which are saturated to a long decades of years, whereas this red dots perovskite which picked up in the last decade has crossed almost, as of now it is 25.5%.
Is the efficiency on a
single junction solar cell?
No. Is it an array of devices or a single element detector?
It's a single junction solar cell. It's not tandem cells. So
not the single junction. Junction is single. I'm talking about, is it an array of devices or is it a single device?
It's a single device.
Single device.
It's a single device.
It's not a fair comparison. Whereas the silicon 21% or 22% is an array, right? Because there you have a lot more loss because of the interconnect and so on.
No. Even in the silicon, when we get in the rooftop panel, it's all 21%. We won't cross more than 21%. These are the lab record numbers, which goes up to 25. Currently, 26.1% is the single junction silicon, crystalline silicon, and the area of that will be around 1 centimeter square. It won't cross to the module levels. Still, it will be in a small area level.
I'm sure even the cadmium telluride last year we have shown 26%, right? From the first solar.
Okay.
The first solar they demonstrated last year something like a 26%.
The cadmium tellurium, as of now, it's around 21%. It has not crossed that.
Last year, maybe it is still.
Okay.
26%.
Maybe.
So what I'm saying is this comparison is a little bit unfair because there it is a whole system which has that much percentage, whereas we are talking about single element, which is lot, which should be a lot.
No, we are not off the page. For example, I'll give the exact numbers. For example, if I use this 2022 number of a perovskite in a large area module, where the efficiency is definitely not 25%, it will be around 20 to 21%. So which is comparable to the large area module of what we get in a rooftop silicon cells.
So what in this material that makes it as a good solar cell material? I understand all these things, but
yes.
What's the physics behind this?
The important physics behind is that it has a very long diffusion lengths and very high mobilities.
Why do they have long lifetime? Why do they have? Is it because you could make them defect free, or is it because?
Oh, nice.
What other things?
So I'll come to the defect in the very later stage.
What causes the long lifetime?
So it's not defect free. We are having a lot of defects, but it is defect tolerant. For example, there can be it's already a tri-element system like ABX3 is there. There can be interstitial or a vacancy. Many defects can arise. Out of them, there are only 4 defects are identified which are prone for very strong quenching of charges. So some of them are lead vacancy, interstitial iodine, and I'll show those, and some interstitial methylamines also. So keeping them as our quenching agents, as a defects basically, all other parameters seems to be like tolerating, because those defect levels are inside the conduction band or the valence band. So that's where we are in a safer side. And the other things is, like, even though it's a polycrystalline nature, one can ask, how can it beat a single crystal silicon? The reason behind this, the softness of this material makes the boundary, grain boundary, such that the charge hopping across the grain boundaries to be pretty easier. So those are some of the explanation which we have come across in order to show that such a wonderful system. It works as a wonderful system. So it has come out in the different direction. We stumbled upon this system. We started out making very good devices, and then we started looking why it's such a fantastic system. So it has come in the reverse pathway rather than.
I'm trying to see if there's any kind of band structure based explanation.
Yes. Yes, the explanation behind the band structure is, one is that there are pretty much defect tolerant for many of them, and it's a direct band gap system, and the ultra fast cooling of charges are pretty fast. Within less than 1 picosecond, all the interhopping of charges happens in the conduction band, and all those seems to be good, like everything intact. Even though it didn't occur in the nature, it's a man-made mineral though, but it seems to be working well. So yes, there has been also some like evolution of a structure where we make a solar cell itself. For example, it started out with just as a DSSC, where we are just keeping this as a die in order to sensitize the TiO2 and then extract the electron from the TiO2. And then it went, okay, let us call, instead of as a die, let us make it as a infiltrate to that. Basically these two are similar to that, where we are infiltrating the perovskite completely inside this mesoscopic TiO2 nanoparticles. So which also led to get a efficiency crossing 20% in early times. And then we went to a very easy way of fabrication, that's a planar structure, where you don't have to worry about even the TiO2, which goes up to 400 degree in order to get a good electron conducting TiO2 Nattes phase. So we get rid of that. Now we are in a case where we just want a small buffer layers for both electron and the whole transport across the perovskite, and this is a pretty easy way in order to fabricate the system. So
it is not under any bias. There is no PN junction in it.
No, there is no, the PN junction. No, it's like we don't call it as a PN junction because there is no P and N system coming here.
You have an electron corrector.
Yes, we have a buffer layers which basically acts as an interface, like a kind of semiconductor junction.
So it gives a local field.
Yes.
So they can separate.
The field is mostly driven by diffusion of charges. It's not the drift which is moving away the charges. And later on, once the built-in field kicks in, then the drift starts. That's the idea behind that. And the film thickness are like 400 nanometer.
Yeah.
So it absorbs everything because of very high absorption coefficient. So with this, so there are three important parameters in solar cells one has to look into. One is the JSC, another one is the VOC, and another is a fill factor, which basically tells about how ideal is your diode, photodiode basically. So out of these three, in the next coming slide, I'll be explaining you on one of the VOC, open circuit voltage. How can you reduce some of the losses when compared to the band gap of the semiconductor, and to attain maximum VOC from the system, the solar cells. So to do that, what we have come across is that, as I mentioned, these are all polycrystalline films, and because of just a spin coating technique, there is always a case where there are some unreacted lead iodide left over it. So it is not completely formed a perovskite phase. There is a lead iodide left over it. And also along with that, there can be some unreacted top surface also, even on this perovskite itself, not on the white contrast, even on the black contrast. There can be some dangling bonds or the surfaces which unreacted or unformed with the perovskite. So to nullify this defects, as we can say, what we have done, we have used a solution process secondary growth technique, which basically you are making another layer on top of this layer, But this layer is little higher band gap than the original bulk of the material. How did we do this? We used just another small change of a organic moiety. We have used a guanidinium based perovskite, which basically helps us to get a little higher band gap, which is of the order of 400 milli-electron volt. And I'll show you the, I think I have not put up that slide, where when we do KPM or KPFM on the UPS measurement, we clearly see there is a little more shift of an Fermi level from the work function of a system when you have a control versus the secondary growth technique in the order of around 400 milli-electron volt. So why do we need this? There's a twofold. One, we are passivating most of the defects which can occur on the surface, and we are also making the Fermi level increase its number. Basically, we're telling that it is making more of an N-type system, which is needed for our planar structure. And hence, because of these two reasons, we could able to jump our VOC from almost 1.1 milli-electron volt to 1.2, which is basically gaining almost 100 milli-electron volt, which in turn give us a power conversion efficiency crossing 21%. So yes, this is an hetero structure. There are many layers. If you want, I can detail on that, but I'll move on to the next topic.
So, sorry, I didn't understand what you about. The VOC increase is possible only when you reduce the resistance of the device. Because usually you lose whatever the amount you gain by the time electron transfer, you lose it to the resistance and you get it. I didn't see anywhere you reduce the resistance.
Yes. What do you mean by resistance? Resistance is nothing but there are some charges which are getting non-radiatively decay at the interface. It can be thermoionic emission or heat, or it can just dissipate into the bulk. What we are trying to do is we are nullifying that non-radiative decay channels. That is the main idea which we are doing.
Because I said the non-radiative decay, you are saying the defect mediated non-radiative.
Yes. So, and the simple measurement is the PLQE. If you do the PLQE of this system versus this system, we clearly see there is a almost like more than 20 times increase in the PLQE, which clearly saying that the defects are getting passivated and the non-radiating channels are getting off. So which is important in order to reduce the voltage losses which can occur in our devices, which basically a contact resistance if you want to consider the accumulated charge across the interface between the electrode and the semiconductor.
If it can be uniformly distributed inside the material, but you are treating only on the surface.
Yes, there is a defect. I'm not denying there is a defect in the bulk, and that's why we cannot cross that Shockley quasar limit. We are still behind the Shockley quasar limit because there are defects in the bulk itself. We want to rectify that also, but for a current being, what we can do is we want to enhance the voltage, photo voltage, and one such thing is just by engineering the surface with a high band gap material. It is a simple way of making it.
It seems to be more that you are efficiently collecting the electrons. That's it.
Yes.
It's not anything to do with this. Most of the electrons were lost at the interface, and you, by removing the interface states, you just collected them more efficiently.
That's precisely what I'm doing. That's what I wanted to do.
Okay, I got it.
But that is not trivial. That's very tricky in this system to do. So, but the question was, is it like you have only changed the surface, or is the overall bulk has changed? Because it's again a solution process technique. So that's an important question which people ask. And what we have come across is we just used our transient technique, but we did direction dependent transient. For example, both PL measurement, time resolved PL, and the time resolved absorption measurement has been done with a direction dependent. For example, this is a system where this is a PMMA side and this is a glass side. That is where is your bulk and this is where is your surface. We pump and probe the system. Similarly, even for when we just reverse that, where the bulk is at the pump side and on the other side we have a higher band gap system. What we have seen is when we look at the time resolved photoluminescence, for a SSG growth film, we see there is a 2 bands coming at early times. That means when you pump this system, there is a 2 excitation which is happening. One is at the higher band gap, lower number, wave number, and the lower band gap, higher wave number. Which basically, if you allow the time to go as the time increases, the PL spectrum goes to the red shift, which basically telling that all the energies are diffusing to the lower band gaps region. Similarly, when I do the same for a glass side, from the glass side, we don't see such a drastic change of PL bands, which is the one confirmation saying that. So only the top surface is basically you are using, and also I didn't mention that we are using a 400 nanometer excitation, which gives a penetration depth of around 60 nanometer for this system. So in the top surface of around 60 nanometer, you are going to absorb all the 400 nanometer photons, but you see there is a completely different transient photoluminescence going on in this. Similarly, the transient absorption also has been carried out, but this is in a transmission mode. So what we see the similar trend for a SSG. When you are doing from a PMMS side, we clearly see there is a redshift happens across like up to 1.8 nanosecond. But whereas if you pump both from the glass side, we don't see any such change in the shift of spectral peaks, ground state absorption of this perovskite system, which clearly says that this is only the surface layer which is having a higher bandgap region, or a different perovskite having a higher bandgap region, and the bulk is still intact. And the energy flows during the evolution of the time, and it also takes up to 2 nanosecond, which is very far from what the cooling time which can take, which is in the order of like 1 picosecond, and we are talking in 2 nanoseconds. So
what is the thickness of that?
Around 400 nanometer to 500 nanometer.
Okay.
Yes, that's a perovskite region. So with this, we'll move on to some interesting other perovskite. That's a 2D perovskite. I already told this is a ABX3 compound where the A side is small methylamine. But there is also possibility that this small methylamine can be replaced with a bulky alkyl amines. For example, I'm just putting a butylamine. By doing so, what you're doing is you're having a slab of octahedrons, lead iodide octahedrons, separated by this organic insulating butyl chains, which basically making it a 2D system, which basically you have a 2D array of octahedron separated by another 2D array of octahedron. And this is what I have shown. That's why you finally end up having a 2D density of states in this system, and you come across all the excitonic nature in this system, which I'll show in the next slide. Along with the just change of the butyl change, we can also change the number of layers which can stack on top of each other in this octahedron, which basically we tell the number of layers here. For example, if you have only one layer between the insulating alkyl chain, or you have 2 layers or 3 layers, we can do all this just by changing the stoichiometry of what we are starting with the system. So all this follows our 2D basic physics, where we clearly see there is as you go for n is equal to 1 system, the band gap increases, and also you start to see the excitonic nature, because both electrons and holes are very confined to each other. And as we go back to the 3D part, you will come back to your 1.56 electron volt band gap. So this is an interesting system, and you have to just use a solution based technique in order to make. But the problem is,
I have a quick
yes.
question on this. I probably haven't done it. Did anyone apply a voltage across the top and the bottom to see the band gap changes?
In which
On this one, this structure, for example. The 2D material, they have the ability to change the band gap.
Absolutely. We can do the electro-optic modulation. We can do that.
Fantastic.
So we can do the electro-optic modulation. We can see the Stokes shifts.
Lot of diverse applications.
Yeah.
You can do the dynamic, you can change it.
Yeah.
You could do this for several. Great.
Very interesting.
I think that will be part of the LED.
No, LED we cannot inject from this C direction. So LED would would like to go the charges to inject from the sides edge states, basically, or it has to just funnel through. Energy funneling should happen.
The insulating.
Yes, because of the insulating part. So, but the problem is when you start with the precursor solution, having like you want to make n is equal to 3 layers, but you won't only end up having n is equal to 3, but you will end up having n is equal to 1, 2, 3, even 50, because it's all solution process, all self-assembly is happening, and we cannot control that. And basically you will end up having something like this in a schematic view if you want to consider. But nonetheless this works well. But what we wanted to do is, we know that these are excitonic in nature and it has a very strong radiative recombination channels, but the edge states are a problem in this. Every edge of this 2D perovskite is a loss channel. So we wanted to passivate it. How can we do this? So we come across what we call a bulk heterojunction of an insulating polymer, and where all these 2D perovskite are inserted on this, inside that. So we use this very readily available polymers, and we put our precursor solution inside this, and we started spin coating the system. The first and foremost observation is the PLQE, photoluminescence quantum efficiency, which drastically increases as you start passivating the edge states of the quantum wells.
So you're talking about the edge state on the top side or
And the edge states. And we believe it's only on the edge. The top is pretty insulating. Like
when you do the spin coat, do they just penetrate through the
when we do spin coat, it self-assembles in all possible random direction. It can be C-axis, can be face on or edge on, we don't know. You can control that also depending on the solvent you used. If the solvent is very volatile or slowly we can control that. It's all self-assembly process which is happening. But yet we can get good numbers. For example, the EQE, when the device has been optimized, we could get the EQE of quite 20%, which is like pretty much one of the high numbers for a solution processed LEDs. Again, the question was, what is happening there?
So what was the n number on this? How much?
So we started out with n is equal to, this is what, 5, but we don't only have 5, we have n is equal to 1, 2, all the excitonic peaks, 2, 3, 4, and also small n is equal to 50 also edges. If you put a log scale, we'll clearly see this, but in the normal scale, you see also the.
But unfortunately, they are all connected.
All connected, but it helps us.
In the sense, it's not like a random sense. It's like they are all connected at only one voltage.
No, they are randomly oriented. In a polymer matrix, it is embedded in a polymer matrix. But the plus point of the here is, if you by chance inject any electrons and holes in the system, for example, for the photoluminescence, you excite the system, it readily cascades the energy to the lower band gap system. That is n is equal to 2, 3, 4 and n layers.
Use it to determine whenever it is giving.
No, it's pretty efficient.
No. It is giving the energy, but it is what happened to the rest of the energy. Well, let's say you start.
That energy we lose
and
out.
you are going to the lower band gap. You are losing. I was trying to say, if you are absorbing it at this, is your VOC equal to this, or is it the smallest one? That's the smallest one.
No, we
You have n equal to 1, 2, and 3.
Yeah.
Let's say the 3 has a smaller band gap, n has what 1 has the largest band gap. What will be the VOC? Will be VOC equal to n equal to 1 or n equal to 3?
So it depends on where the n is staying. I'll come to the next slide. You will understand what is happening. So if it is completely randomly oriented, I think if you consider it's a parallel junction of all the diodes, then it will try to go for a lowest possible VOC. But it is not the case. We can play around that. Yes. So but the interesting part here is again what is happening. So we see again the transient absorption spectroscopy of that. We clearly see all the higher band gap quantum wells readily cascades its energy to the lower band gaps. So what is happening is you excite the system, the photon, the exciton which generated in n is equal to 1, 2, 3, 4 layers, which readily push the energy. That means there will be a FRET or a Dexter kind of energy transfer which happens to the lower band gap system. And where lower band gap, we know from the bulk measurement, it undergoes bimolecular recombination, and which is in a very efficient way. So this is the idea behind this technique. But what we can play around VOC, we didn't increase the VOC, but this is another interesting example what we have done here. So when we see any color sensor or your camera in your mobile, so each pixel in your software which you see, it's a combination of 3 pixels, 3 photo detectors. One with the R filter, G filter, and the B filter will give you 1 pixel basically. So but the idea behind this work is, why can't you increase the density of pixel here by just having a single pixel which gives you a photon detection itself. So ideally when you do your camera, it only gives you voltage reading, but it won't tell you what is the energy of your photon. To do that, what we have done is, we have done a graded bandgap structure, which basically using the same 2D, 3D quasi mixture, but we have done a hot cast technique where we intentionally choose a solvent, and we also heated the substrate to a certain degree so that the self-assembly of a 2D starts initially, and as time evolves, the 3D goes to the top because you are left over with only the amines, methylamines. Because of that, you started having a graded structure, in a kind of graded structure. So we established that graded structure just by the directional dependent PL. We clearly see when you excite from the bottom side, we clearly say there is higher energy photons are coming. when you excite from the other side, we clearly see there is a dominated by the lower energy photons. Even the confocal measurements in the z-axis, which clearly shows at the bottom we are dominated by the, it's a confocal measurement, the two channels, one above 630 nanometer, another one is a below 630 nanometer photon counts, and we which is having a red and green, and we overlaid the every confocal images here. So what we see at the bottom, we see mostly a green, which basically telling everything below 630 nanometer is coming. And as you go to the top of the film from this side, we see there is mostly dominated by the red region, which is like a low band gap system.
Is the area of the curve B is not the same for both the colors?
No, both are same.
Same intensity, or they absorbing different amount or what?
Same intensity light, same source. You are just changing the sample.
So which means you are losing lot to the frontal, or what happens? Why is that you are losing in the brown case? You are losing more. You are not generating as many
It's
electrons.
normalized.
Normalized to what?
The two are normalized at one, so it's like you really need the real values to compare the area. It's just weighted to the shorter
Yes,
wavelength.
to show where it is coming.
Exactly. The total
So there
area
is
is
a
not
glass
there.
also is there, right? Glass also will influence.
No, we don't want an absolute number here.
Yeah,
We want to
it's not
show what is the
absolute number.
trend of a PL, which is coming from the bottom or from the top. The trend is clearly shown here that it is dominated by the lower band gap region versus where there is a component of higher band gap coming in.
Reference to 800, what happened to the extra?
Yes.
Okay, it makes sense.
Yes.
I think we have another,
I'll run fast. How many minutes?
so maybe we'll allow him to make the presentation complete and then we'll ask more questions.
Yes. How many minutes I have? More?
10 minutes.
10 minutes. Okay, I'll run through fast. So what we have done, again we have done a transient absorption spectroscopy of the system, again the direction dependent. We clearly see when you go from the glass side, we clearly see the population at early times within 1 picosecond. We see all the charges are getting ground state bleached, and within like tens of picosecond everything is passing to the lower band gap region. But whereas when you do the same from the perovskite side, that is from the top side, we don't see any excitation because our optical depth is pretty small, within 60 nanometers. So that's why we see already a dominated lower band gap regions. So this is a signature, but what about the device? Where did we get the signal? So to do that, we carefully choose a hole only device where the current is read will be only from the holes, where we have done this graded structure where both the sides of the graded structure we have coated with the hole transport buffer layers, which allows the hole transport to occur in this region. So what we have done, if you consider the case where you are having a green photon versus red photon, if you put a green photon which basically absorbs in the front end of the device, will lead us to diffuse the holes to the respective P dot PSS and gives you certain kind of current, which we call it as a positive current. What happens if you put a red photons is that it can penetrate through because it doesn't absorb with the high band gap region, and the photons generates the charges at the rear end of the device, and the hole diffuses to the other buffer layer and gives rise to a negative photocurrent. So because of this, we basically end up having, if you change the wavelength of the region, we get a combination of both positive and negative in the middle region, whereas in the above 650 we get almost the negative, when in the below 400 we get all the positive. So which is a way we can basically say that we have made a single pixel color sensor, where even a single pixel not only gives you just a photon count, but also gives you can also give an analysis of what is the energy of a photon. So with this, there is also another important aspect, that because of this strong ionic conductivity of this material, we have a very varied numbers in terms of its mobility. So for example, it all the way you can say it's around 0.4 to almost 600 centimeters square per volt second is the number which they have done. So this is real disturbing because we don't get real numbers in this, because the main problem is the fabrication has been done by different people, and the grain size, the grain boundary, all these effects will vary. So what we have done, we have planned for a non-destructive way or non-contact way of measuring this diffusivity. What we have done, it's a confocal arrangement. We have used the pulse laser to excite a localized spot which is less than 1 micron, and we use the ICCT, which is an intensified gated camera, in order to see how the PL evolves with time. So for that we consider the system again ABXC compound, but here A system we intentionally changed in order to identify what is happening in their mobility, and which basically are lead bromide systems, and these are microcrystals. We intentionally chose microcrystals in order to like nullify all the effects which can occur from the grain boundaries. So this is a real data. So this is a local excitation spot at time 0 when the pulse is arrived or just left the pulse. Then as you leave the system, it evolves with time. As it evolves with the time, you can see the PL is also distributing in the lateral direction. What it is basically telling, the charges are diffusing across the system, and you are getting a PL from that because it's a bimolecular recombination. So what we have done, this is a ray, we have took out our profile across the center of this circular spot which is expanding, and we use small simple mathematics. So it is, if you consider this evolution, if you consider the one dimensional charge motion of the system, so you can get rid of many terms. For example, after the pulse arrives, there is no generation term. We can get rid of generation, and if you take care of the radiative and non-radiative effective lifetime to reduce to tau, we will end up having a very simple equation. The solution to this is just a Gaussian function, which basically anything which is moving in a Gaussian fashion, one can establish their diffusivity by finding out their MSD, which is a variance, difference of variance with respect to time 0, square of variance with respect to time 0. So this is an equation which we have used in calculating the MSD and diffusivity, and hence by using just Einstein equation we can estimate what is the mobility in this system. Excuse me. So this is a fitting. We calculate the MSD versus time, and what we get, we intentionally choose a power expansion. What we get is an alpha which is in the range of 0.63. So what basically alpha is telling, if it is alpha is 1, it is a diffusive nature. If it is more than 1, it's a super diffusive, which happens at a very early time. And if it is less than alpha, less than 1, it is a subdiffusive nature. And we obviously see there is clearly a subdiffusive nature, and this is what expected. And also we wanted to see, is there any photons recycling component which is coming in the system, but we didn't see any strong photon recycling component. For example, this is the same crystal when the PL has been acquired across the crystal, and this is a PL spectrum. We can see the y-axis is the PL spectrum across the position. Only at the edges we see that there is a wave guided photon counts rather than any photon recycling, very minimal photon recycling which we neglect in the system. With all this case, we calculated our mobility, and it turns out to be in the range of like 58 for a FA and 52 for a MA based system and 81 for a CGM based system. So this is one of the non-technique wave, and it is in the average of not in a very like if you have a range of numbers, and this seems to be a reasonable number of estimating the mobility of this charges in this system.
For the same system with the electrical properties, how much you got?
So FETs are in the range of 1. FETs are pretty, always when you make an FET, the mobility ranges comes down. For a MAPBR, it is even in 0.6 or 0.1 into 0.6 range. But for a MAPB I3, it is in the range of 1 centimeter square per volt second. It all depends on how well is making a transistor. But yes, and the last topic is this, the important aspect, that's what is the nature of this ionic motion which is happening in the system. So we try to probe this. So as I was saying, there are different kinds of defects which can have, because it's a 3-element compound, and some of them which I'll put across firstly is that there is a lead vacancy, is a strong quencher of a volts basically, and also interstitial iodine. These are the two culprits which basically quenches our charges. What we have done the photoluminescence measurement. Basically when you excite the system, the volt gets quenched with these defects, and which leads us to different analysis which we are going to do. So the measurement setup is again the confocal with working transistor devices across and we apply external bias, and we try to see what is happening when you before bias and after bias, what are the PL changes happens in the channel of a FET device. So what we see here, these are the cathodes and anodes which is going across the device.
The resolution of your confocal?
It's less than 1 micron. We are not in that 200 nanometer region. We are okay because this channel length is in the range of 10 micron and above. What we see, the before bias, we see there is a pretty uniform PL across the channel, but as you start applying the bias, you start to see there is a PL changes which is happening. So to clarify this, to make it appealing, we have plotted here. So what happens, this is a before bias condition. As you apply a bias, you start to see there are changes in the PL profile across the channel. What we basically telling, that across the positive electrode, your PL is getting quenched basically, and the negative, it is not much affected. So the similar things happens, but we also done and also if you keep the same system, like these are just for a 30 seconds of bias, but if you allow the same system in a dark, what happens, these ions redistribute back and you will get back your PL which is starting in the condition. We might have to wait for more than 1 hour in order to get back the same PL, but in the order of like 12 minutes it can get back to its original PL position. So what is happening, we intentionally changed our concentration of defects by just changing our precursor concentration, intentionally change the system where we have more of AX versus BX2, which basically gives this is a condition where we basically gives both interstitial and the lead vacancies to be high, whereas in the other case, which it doesn't affect those those defects, but it might increase the A side cation. But when we change this system, we clearly see there is a very drastic PL profile change upon bias. That means both this interstitial iodine defect and the lead vacancy defects are reason for very strong PL quenching. Basically, when you apply a bias, all the interstitial iodine are starting to move to the, which is negative in charge, which start to move to the positive electrode, which basically quenches all the PL which originates here. And increase in PL can be due to a sweeping of all the interstitial, already pre-existing interstitial iodine. So this is a system which we have concluded, and some conclusion which I have drawn across here. And with this I'll end the talk. So yes, the perovskite based solar cell is a very potential alternative for a conventional, because of the one important reason is it's already crossed 25% in its power conversion efficiency, and it's pretty affordable in making the fabrication process. And different nanoscale perovskite can be used for different optoelectronic devices. For example, I've used to show LEDs and single pixel color sensors. And solution processability of these all kinds of perovskites allows us to make a large area roll-to-roll module level fabrication, and that's a way to go forward for this. So with this, I would like to thank my collaborators, Professor Richard, Enning, Felix and Sean and Yu Cheng from Cambridge, James and Safa from Imperial, K S Narayan and Ganesh from JNCASR, and Henry and Aditya, who is in IIC now, from Oxford University. Thank you all for your kind attention.
Questions, maybe we can start.
To the nice talk. So I think when we talk about perovskite, we'll all come to a basic question: what is the stability of the cell? So what would be the stability, and what are the measures that what can be?
Yes. So basically, the stability, the main culprit in the stability is the ionic motion. So ions are the defects are the reason which tries to make this deposit to the one of the electron which start to corrode, and that lead to a degradation. So what we have come across is we try to use the stoichiometric approach. One is that, and we also have a surface passivation and the defect passivation approach, and also we also use some 2D based perovskite which are little prone for this defect motion. There are strategies we use in order to increase the longevity. Currently, as of report, one estimates that it has a extrapolated value as a lifetime of 9 years. So which is reasonable in order to come into the market. Yes, when we start making devices, it will die within a day, but when you start optimizing the device, it can stay for a very long time.
Any questions?
I think in continuation with that question, you showed that PL quenching in between. So since these perovskites are known to undergo structural instability, how are you making sure that it is not some sort of MAI or lead iodide where it is the film is intact, only the defects which are playing the role there?
Yes. So the simple example is here itself. We can see the same experiment which we have done. We intentionally not touched upon increasing the interstitial iodine. We intentionally reduced the interstitial iodine here, which drastically changed our profile. You see how much the PL has changed versus this. So this is one small example which I can give. Similarly, if you clearly optimize, now we have used, this is FAMACS based system where only iodine has been used. But if you start using bromine, which gives us structural stability for an octahedron tilting itself, which reduces the hopping of defects.
That also can't put the ion migration, like halide ion migration, that will kill the
No, it's true. If you use like 40-60%, there is a very strong iodine migration, halide migration which happens. But if you are in a like 0.3%, or 0.5%, there it actually basically increases the stability of the system. It's all working in basically unit cell wise, where we are trying to change the volume of the crystal itself and also the tilting of the octahedron, which basically, for example, if you consider only FA based FAPBI3, it basically goes to yellow phase. So if you want to be kept in a semiconducting black alpha phase, you have to just add like 5% of a MA. So which basically what is happening, you are trying to play with the unit cell of the perovskite, which basically keeps your structure.
Do you think compared to FA and MA, CS would be a better cell because of its size?
Absolutely. But the only problem is the CS at the room temperature, it undergoes the phase change.
CSIMTP.
Yes. So we want to use some other alternative in order to keep the structure in a perovskite phase.
Is there any direct evidence of these interstitials being observed by any microscope technique?
No.
I know that there is a difficulty in doing the microscope itself because the moment electron beam falls, it decomposes. Are there any other methods? For example, I think you were roughly including 10% of interstitials on either side.
Yes.
So, what is the guarantee that the interstitial or vacancies are the ones which are contributing for this?
No, the lead vacancies are as a very high hopping formation energy for an hopping. So because of that, we generally have a less mobility of a lead vacancy. That one can assume that. But if you ask what kind of measurement can lead us to know this is the case, I think we have not come across to that point. With the known parameters, we try to establish this can be the case by changing the stoichiometry like this.
Any further questions? Of course, we can ask the questions. I'm going to give a cup to him as a memento, so he will straight away go to the coffee.
Coffee is outside.
So you can join him.
I needed one memento actually. Thank you.
Thank you.
Thank you very much.
Nice talk.
Thank you.